All right, greetings everyone. Welcome to the second part of the video for section 3.2. We're going to talk a little bit more about finding derivatives as functions using the limit definition of the derivative, and then also look at how the derivatives relate to shapes of a graph. Okay? So, I'm going to come back to this problem, which I know I said before you would be doing as classwork. However, as I thought about it and based on the questions I got, I figured that this one might be a good one for us to do together. So here we're supposed to find the derivative g prime of t of the function g of t equals 10 over t using the limit definition of the derivative. And remind ourselves, remember our limit definition says that we take the limit as h approaches 0 of, in this case, it would be g of t plus h minus g of t all divided by h, right? And so to do that, we first need to find g of t plus h and then g of t. And we know g of t would just be the function itself here, g of t plus h. Well, notice the t plus h is in the place of our variable there. So this would just become 10 over, instead of 10 over t, it would be 10 over t plus h. So we now plug that stuff into our limits of limit as h goes to 0 of 10 over t plus h minus 10 over t all over h, which you might look at and think, holy buckets, that looks like a nightmare. And it's not. There's some work we need to do here, but we can definitely handle this. And I'll tell you that for right now, I'm going to forget about the limit. I'm just going to focus on simplifying this fraction we have here, or this rational expression, okay? So I'm going to erase some stuff because we're going to need a lot of room here. Okay, and let's actually even for now break this down even more, and let's look at just the numerator of this fraction, the 10 over t plus h minus 10 over t. Now I know there's some variables along with numbers and all of those sorts of things there, but notice these are just fractions. Okay, and so we have to think about when we subtract two fractions, how do we do that? Well, we have to get a common denominator, right? And between t plus h and t, I know the fraction on the right has a t in the denominator. And so you might think maybe we can just add h, but that's not the way fractions work. So in this case, this is one where we actually need to multiply the two denominators to get our common denominator. So it'll become t times t plus h. And then we'll also have t times t plus h as the denominator here. On the left-hand side, we had to multiply the denominator by t to get our common denominator. So we multiply the numerator by t, so we'll have 10 times t up there. In the second one, we had to multiply by t plus h to make the common denominator. So we'll have 10 times t plus h. And then now that we have a common denominator, we can combine the numerators. And when we do that, we're going to do a little simplifying. Up here, we'll distribute the 10, but also notice there's this negative sign out here, so that needs to go with the 10. So we're actually going to distribute a negative 10. So we'll end up on the top of our fraction as 10t minus 10t, and we distribute the negative 10, and then a minus 10h all over t times t plus h. And then notice on the top, we have a 10t and a minus 10t, so they'll cancel. And I also realized I wrote the wrong thing here. This should not be 10t, this should be 10h here. Okay, so we have a minus 10h left on the top. All right, so yeah, this is really messy. Let me just rewrite what we have. So we have negative 10h over t times t plus h right now. Okay, so that's what the numerator over here became, and by over here I mean in our limit, but there's still that h in the denominator. So what this is going to look like now, then is we're going to have on the top now, we've made that negative 10h over t times t plus h. And we have the h in the denominator. So notice we're dividing with fractions here, right? We have a fraction on the top. We're dividing by a fraction on the bottom, which that fraction on the bottom we can make as h over 1. So what this will become now then is we will have negative 10h times t plus h times, remember when you multiply with or divide with fractions, you keep the numerator the same, divide or flip the bottom and then multiply. So this will become, instead of h over 1, 1 over h. And notice when we do that then, h is here, can cancel. So we'll end up with negative 10 over t times t plus h. Okay. So lots of fun simplifying and all of that to make our limit a little bit easier to work with. So again, this is what we have now, negative 10 over t times t plus h. Let's go ahead and erase some stuff out here. So now we see that our limit has become the limit as h approaches 0 of that thing we just had. So negative 10 over t times t plus h. And notice here now, right, we can actually input 0 in for h. That's in the domain of this function now, so to find our limit. So now our limit will become negative 10 over t times t plus 0, which is just going to become negative 10 over t squared. Okay, so our derivative here, write it up here at the top, just to use the notation. Okay, so our g prime of t, remember g prime means the derivative, is equal to negative 10 over t squared. All right. Fun times, right? Fun times. Okay. Let's talk about the shape of a function and how that relates to the derivative. Okay. So you'll see here in the PowerPoint, I've got a link to a Desmos animation that I'm going to pull up here. So here's what we've got going on is in this picture that you see, the red function here, that's our function f of x. This dotted black line here, that represents the tangent line at that specific point that's lit up here, the red one. And what you're going to see once I start doing the animation here is that there's going to be a yellow or orange function that comes here that's going to trace out the derivative. So we just saw the derivative can be described by a function where we can plug in any point along the function. It'll tell us the slope of the tangent line. And we're going to use this to kind of draw out the derivative here. Now, something I want you to notice is whether the slope of the tangent line is positive or negative as we move along here. So notice right now, this dotted black line is sloping up from left to right. So the derivative is positive. So watch what happens as we start to slide this along. So notice as it's moving, the slopes of all these tangent lines are positive. And so because of that, we see the outputs here of the orange function are positive. However, those derivatives those slopes are decreasing, right? They're all staying positive, but they're getting smaller, which is why the function is going down. And we see as we continue along, right, they continue to be positive, continue to be positive, continue to be positive. But then we get to this point right here-ish. And notice what happens here. The slope is positive, so the orange function is above the horizontal axis. But then as I tick over to here, notice that line starts to slope down, and notice what the orange function has done now. it's gone below the horizontal axis because the slopes are now negative, right? And as I trace along here, you'll see that it's going to stay below that horizontal axis because our lines are sloping down, and now it's even more obvious, right? They're staying negative, 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 but then they start to get less negative here, and then we get to this point right about here. Notice still negative, and then okay, the line switches to sloping up. So now that we see that we have positive slopes of our tangent lines, and it can continue on from there. Okay, so this orange function here now becomes their graph of our derivative. Okay. All right, let me back it up and trace it out just one more time so we can see. So again, positive slopes, so we see our function is above the horizontal axis. We get to this little local extrema here, and notice it seems to switch from positive to negative, so then the function is down below the horizontal axis. As we go along here, we get to this point, and again, it kind of stops being negative, and they become positive, and then we continue on. All right. So we see, again, there's a relationship, or we can kind of see how to draw out the derivative based on the slopes of the tangent lines along a function. Okay, so let's look at how this would work for something like this. And actually, now that I see this, this is very similar to what we were just doing, but or what we just saw, but I think it'll still be helpful for us. So notice, if I'm going to draw out the derivative here, well, I'm going to kind of divide this into pieces, the function f, based on where the extrema are. So I see that there's an extrema here, an extrema here, whoops, not there, here, and the graph is doing different things in between those lines I just drew, right? So notice, first of all, to the left of the first line, any tangent line I seem to draw, notice that it seems to be sloping up. So all the tangent lines there have positive slopes. We get to 1, and then to the left of that, it looks like all the slopes are now, all the lines are now sloping down. Whoops, not that one. Okay, so then we have negative stuff there. And then we get to 3 and continue on past 3, it looks like we again start to get positive sloping tangent lines, right? So how will that help us draw the derivative? Well, we see for this first piece here, right, from 0 to 1, everything is positive, right? So all of our slopes have to be above the horizontal axis, and they seem to kind of decrease as we go along. So we might see something like this. And then at 1, there seems to be a change, right? They change from positive to negative, and they stay negative till 3, which is where they change again. So between 1 and 3, we need to be completely below our horizontal axis. And then at 3, they changed back to positive. So now we have this sort of thing. So that kind of, again, like I said, seems very similar to what we just saw with the animation I had. Okay. All right, let's look at one more of these. So here we have something that looks like a piecewise function. And I say piecewise because I see a couple of different pieces here. I see a line, upward sloping line here, and then looks like a horizontal line there. So that's what makes me think this is piecewise. And let's take a look at the slopes here. Let's look at the first part, all right? This here. Well, this itself is a line, right? And we actually already know the slope at every single point, or we can find the slope at every single point, right? If we just look at, say, rise over run between a couple of points here, it looks like I can go up 2 over 1, up 2 over 1. So it looks like from 0 to 2, we have a constant slope, and that constant slope is 2. So when we go to draw the derivative from 0 to 2, we should have a horizontal line, I believe, that is at 2, because it's a slope at every point along there. Now notice at 2, we have this corner point. Do you guys remember, does the derivative exist at a point like that? Hopefully you're saying no as you do that. And sorry, I'm trying to clean up my derivative. So remember, they points are not differentiable there, so we can't have the derivative exist. So as I draw the line here for the derivative, I'm going to put an open dot at 2. And then notice what happens after that, right? We have a horizontal line now, which a horizontal line, what's the slope there? Yeah, that one's always 0. For values of x greater than 2 here, we see that our slope is a constant at 0. So that'd be right along the horizontal axis like this. We still have this open dot here. So here, our derivative of this piecewise function actually also ends up being a piecewise function that has a horizontal line at 2, and then it breaks, and then it has a horizontal line at 0. Cool, huh? Yeah, I think so. All right, that's all I have for you for now. Thanks for watching.